Welcome to week 7 of the live problem solving sessions for the course Introduction to Wireless and Cellular Communications. I am your instructor Sachin from the EC department at the Indian Institute of Science. Yesterday, due to some reason, I was unable to record the session that I actually conducted. Since there are people who don't attend the live sessions and only see the video pre-record video recorded and posted on YouTube. I am recording the session again. I'll try to keep the pacing identical to what we did last time. So I'll show you the question and then I'll give you the answer after a pause. If someone is watching this on YouTube, you can skip ahead a few seconds after each question. Okay, the first question we solved yesterday was given channel coherence time and coherence bandwidth are 16 microseconds and 100 kilohertz respectively. 16 QAM modulation is used for communication to achieve 1 megabits per second throughput. Which of the following is true about the channel? Is the channel slow fading and frequency selective, fast fading and frequency selective, slow fading and frequency flat, or fast fading and frequency flat? So we can solve this problem by comparing the quantities given the coherence time and coherence bandwidth with the symbol duration and signal bandwidth. The symbol duration is 1 over the symbol rate, but the symbol rate is the bit rate divided by log 16 base 2 because we are using 16 QAM modulation. That means each symbol is of log 16 base 2, which is 4 bits. And here the throughput is 1 megabits per second. So that's the bit rate. And once we find the value of Ts, if Ts is less than Tc, then it's a slow fading channel. If Ts is greater than Tc, then it's fast fading. Then we calculate the bandwidth of the signal as the symbol rate, which is which is the inverse of symbol duration. We calculate it for the first part. Then if bandwidth is greater than the coherence bandwidth, the signal bandwidth is greater than the coherence bandwidth, it's a frequency selective channel. But if the signal bandwidth is less than the coherence bandwidth, it's a frequency flat channel. So you can compute Ts and B, and using these hints figure out whether it's a slow or fast fading channel and a frequency flat or frequency selective channel. Next question, which one of the following Doppler spectrum plots corresponds to a line of sight scenario? This has been explained properly in lecture 29, and I would urge you to go and watch lecture video for lecture 29. Question 3 is which of the following statements is or are true for an interference limited system given that C is the carrier power, N is the noise power, and I is the inference power? And the statements given are statement 1, C over N is much greater than C over I. Statement 2, C over N plus I is approximately C over N. So pause the video and try to solve it yourself. I'll come back in a few minutes and give you the answer. Okay, question number 3. The solution to question number 3. Since the system is interference limited, I is much greater than n. You can take an example. Suppose AC is 1 and n is 0.01. I is much greater than n for interference limited, so I can take I is 0.1. And you can see that C over n is 100, C over I is 10. So C over n is actually much greater than C over I. But C over n plus I is approximately equal to C over I, not C over n. C over n plus I is 9.09, which is much closer to C over I than C over n. Then question number 4 is, given the maximum Doppler shift in a channel is 100 Hz, it is required to simulate the channel using JX model with 50 oscillators. Which of the following is not an oscillator frequency? The options are rounded up to 2 decimal values. Here the oscillation frequencies for JX model are given by Fn is Ft, which is the maximum Doppler shift, into cosine of 2 pi n over 4 n0 plus 2, where n0 plus 1 is the number of oscillators. So n0 plus 1 is 50, n0 is 49. So f1 to f49 you can calculate using the formula, and then f50 is the Doppler shift, maximum Doppler shift. So you have to, either you can check one by one for the values of different values of n, or you can plug in the values given in the options. One answer, 100 Hz, is one of the oscillator frequencies because fn0 plus 1 is equal to fd. Then you can find, you can substitute each of the options in place of fn and find out if the answer you get by solving the equation for small n is an integer or not. If n turns out to be an integer when you solve the equation, then that frequency is a valid oscillator frequency for the X model. Question number 5. Which of the following is true about the Walsh-Hadamard matrices? Walsh-Hadamard matrices are matrices you get by rearranging the rows of a Hadamard matrix. For example, for a 4 by 4 case, this is an example of Hadamard matrix, and this would be a Walsh matrix. Now, for the general proof, you can search in math textbooks or in the lecture videos. Or from the example, you can see that these are symmetric and orthogonal matrices. Question number 6. Which of the following is true with respect to Smith method and Clark and Gans method? Smith method requires more computations. Clark and Gans method has a more computational complexity. Smith method can generate fading waveform for any duration, none of the above. Again, I'll try to think about it and try to find out from your lecture notes. I'll come back in a few minutes and give you the answer. So I'll give you a few hints to solve this question. First is that the Smith method uses FFT or IFFT. So is FFT does FFT reduce the number of computations required, or does it increase, or is it the same? Based on that you can answer whether A and B are correct, which one of A and B is correct. Then the next fact is that using Smith method we can generate fading waveform for a duration 2 power n times ts seconds, where n is the size of the FFT and ts is sampling period. You can't do this for any arbitrary duration. So that rules out option C. You have to decide between option A and B and also D. For question 7, it's again a theoretical question. You can refer to lecture 31. All I can say is that C is a true statement. So you can look at the other options A, B and D again. Question 8. Consider a base station and a mobile system with two antennas. The transmission from the base station is picked up by both antennas, which experience different channel conditions and hence different values of instantaneous SNR. The SNR for both antennas is below the threshold at which the signal can be properly detected. Which of the following diversity techniques may lead to proper detection of the signal? A. Selection diversity, B. Optimal diversity, C. Both A and B, D. None of the above. So go back and look at your lecture notes now and see what selection diversity and optimal diversity are and compare in the particular given scenario which of them is good or are none of them good. So you go back and look at your lecture videos. If you're following along, I'll come back and answer the question in a few minutes time. Alright. So in this question, suppose that the SNRs of the two SNRs of the received signal at the two antennas is SNR1 and SNR2. We are given that both the SNRs are below the minimum required SNR for the receiver to work properly. So let's call that SNRT, SNR threshold. Both SNR1 is less than SNR1 and SNR2 are less than the threshold value. So selection diversity will give you an SNR which is maximum of the two SNRs. So in selection diversity, it's actually at every instant of time it looks at which of the antennas is giving better performance and selects that antenna. Whereas in optimal diversity, you get a SNR which is the sum of the two SNRs. So in this case, since both the SNRs are less than the threshold value in selection diversity, you actually will not be able to detect the signal because the max of SNR1 and SNR2 will also be less than the threshold. But the sum may or may not be less than the threshold. So you may or may not properly detect the signal, but and there is a chance. So that's why the question asks which of the following diversity techniques may lead to proper detection. Okay. In this previous question, assume that one antenna experiences SNR above the required threshold while the other does not. Which of the following diversity techniques may lead to proper detection of the signal? Again, we are comparing between selection diversity and optimal diversity. So you will use the same fact again, that in selection diversity, if you do selection, the diversity you get is max of SNR1, SNR2, that's the SNR of selection diversity, and SNR of optimal diversity is SNR1 plus SNR2. But in this case, one of the signals has an SNR greater than the threshold. So selection diversity will definitely choose a signal. So it's max of SNR1 and 2. If, let's say, without loss of generality, you can say SNR1 is greater than the threshold value. And if SNR2 is above the threshold value, then both of them, whichever, regardless of which one is the maximum value, both of them are above the threshold and the signal is properly detected. If SNR2 is below the threshold value, then the max among the 1 and 2 will be the first one. So SNR1 will be your resultant SNR, which is above the threshold, so the signal will be detected. So either way, the signal will be detected. And since one of the SNRs is greater than the threshold SNR, in optimal diversity, which gives you the sum of the two SNRs as the resulting SNR, since SNR is a positive quantity, if one of them is above the threshold, then the sum is also above the threshold. So in this case, both of them will work. Question number 10. Compute the probability that the output SNR of a selection diversity system is 15 dB lower than the average SNR of each branch when using 3 identical receive antennas. So here they are given that 10 log of gamma threshold is 10 log of gamma. Capital gamma is the average SNR minus 15. So this is in dB scale. That means 10 log of gamma threshold by capital gamma is minus 15. Gamma threshold by capital gamma is 10 power minus 1.5. We have seen in the lecture that the probability that gamma selection is less than or equal to gamma threshold is given by the formula 1 minus e power minus gamma threshold divided by capital gamma, the whole thing to the power m, where m is the number of receive antennas. So let me solve this for some other value. So this is approximately 1 minus 0.99 whole power 4. This is 10 power minus 6. That's the outage probability. Next question. Selection diversity is not helpful in which of the following scenarios? All the antennas are weak in a noise limited system. We saw this in question 8. When both the antennas are weak, so both SNR1 and SNR2 are less than SNR threshold, then we saw that selection diversity was not useful. So straight away we know that option A is correct. That is, if all the antennas are weak in a noise limited system, selection diversity is not helpful. To check whether B and C are correct, B antennas are correlated, C we are in a fast fading scenario. I'll give you some hints. If antennas are correlated, then both antennas have a high chance of experiencing low SNRs. So you can use that fact to guess at whether B is whether in the case of option B selection diversity is useful or not. Then selection diversity needs continuous measuring of SNR at all antennas. Then you select the best among the antennas and then perform detection. All this has to happen within a coherence interval. But in a fast fading scenario, the coherence interval is very small. So all that to do it, it might not be viable. Based on that, you have to decide whether it is helpful in a fast fading scenario. Question 12. Consider that BPSK symbols are sent from the transmitter and a 4 antenna receiver is deployed. If only one is used, PE is 3.87 into 10 power minus 6 in an AWGN channel. If all 4 are used with selection diversity in a relay fading scenario, what will be the outage probability given the minimum SNR required for successful reception is 3 dB. The given PE is Q into square root of 2 gamma AWGN. So the SNR at which you are transmitting your signal. You can find that from the formula for relay fading in AWGN channel. The probability of error is Q function of square root of 2 times the SNR. So that the SNR turns out to be 10 if you plug in the values. Then we know that for Rayleigh finding average SNR, capital gamma is expected value of mod z square times gamma AWGN, and as usual we take mod expected value of mod z square to be 1. So in this case capital gamma is 10. Then like we did in the previous question, P outage is P gamma less than gamma threshold, which is 1 minus gamma threshold by capital gamma power m. Here m is 4. Gamma threshold is 10 power 3 over 10 in the linear scale because the minimum SNR required for successful reception is 3 dB. We know the value of gamma threshold, we know the value of capital gamma. So we can find the probability of outage with this formula. And question 13, it's a simple question that you can answer yourself. You can refer to lecture 33. That's where you'll find the explanation and the concept needed to answer this question. Question 14. Consider the case where co-phasing is implemented using 4 receive antennas. Assume that the average SNR of each antenna is the same, capital gamma. What is the average SNR of the signal obtained by co-phasing? That is expected value of gamma co-phasing. Try to work this out yourself. E of gamma co-phasing will turn out to be 1 plus n minus 1 times pi over 4 times capital gamma, where n is the number of receive antennas. For the different receive antenna diversity schemes with identical antennas, what is the ordering of gamma MRC, gamma co-phasing, and gamma selection? Try to go back to the lectures and find the answer yourself. I'll come back in a few minutes and give you the correct answer. Or I'll give you hints to solve the question. 1 plus 0.5 plus 0.67 0.667 plus 0. That turns out to be 3.35. So this is 10 times 3.35, 33.5. Gamma MRC is the simplest to calculate. It's 4 times 10, which is 40. So clearly you can see gamma MRC is greater than gamma cophasing, which is greater than gamma SC. Then for question 16 and 17, you can refer to lecture 33. These are just true or false questions. Right, that's it. Hope this is helpful for solving the assignment this week. So just for logistics purposes, I will keep this video on for another half an hour. So that's the duration for which the actual live session was conducted. So I'll keep this recorded video too about the same amount of time, stretch it out to the same amount of time. If you have any questions, you can post in the Q&A section of the course. There's a tab at the top called Q&A. Of course, I will be answering questions only related to the problem solving sessions that I have conducted. If you have questions regarding the course, anything in the course, then TAs from the actual main TAs for the course will answer. Good luck with this week's assignment. let me go through all the questions one more time. One given channel coherence time and coherence bandwidth, and that it is a 16 QAM modulation achieving 1 megabits per second throughput. Which of the following is true about the channel? We solve this question by finding the symbol duration Ts and signal bandwidth B. Then if Ts is less than Tc, it's a slow fading, and Ts greater than Vc. Tc means that it is fast fading. B greater than Wc means it's frequency selective, and B less than Wc means it's frequency flat. For question 2, refer to lecture 29. Question 3. Which of the following statements is or are true for an interference limited system? Given that capital C is the carrier power, capital N is the noise power, and capital I is the interference power. And the two statements are: statement 1, C over N is much greater than C over I. Statement 2, C over N plus I is approximately C over N. Since the system is interference limited, I is much greater than or equal to N. And you can just take an example. For the same C we have taken 1, I is 0.1. Since N is much less than I, N is 0.01. C over N is 100, which is much greater than C over I, which is 10. And C over N plus I is 9.09, which is approximately equal to C over I. And the larger I is when compared to N, the lesser effect N will tend to have. Given the maximum Doppler shift in a channel is 100 Hz, it is required to simulate the channel using Jake's model with 50 oscillators. Which of the following is not an oscillator frequency? The options are rounded up to 2 decimal values. We know that the oscillation frequencies of Jake's model are given by Fn is Fd times cos 2 pi n over 4n0 plus 2, where n is 1, 2 up to capital N0, and F capital N0 plus 1 is F0, which is equal to 100 Hz, Fd, which is equal to 100 Hz. Capital N0 plus 1 is the number of oscillators, which is 50. Then we substitute each of the values in the options and find out which of them does not corresponding to an integer value of small n. Question 5. Which of the following is true about the Walsh-Hadamard matrices? They're symmetric matrices, they're orthogonal matrices, they're both symmetric and orthogonal, none of the above. You can see an example of a Hadamard matrix here: 1 1 1 1, 1 minus 1 1 minus 1, 1 1 minus 1 minus 1, and 1 minus 1 minus 1 1. A Welsh matrix is nothing but a rearrangement of the Hadamard matrix, rearrangement of the rows of the Hadamard matrix. So you can see that the rows are identical. So exchange of rows doesn't actually change. Does it change the nature of symmetry? Yes, yeah, when you exchange the rows to get a Walsh matrix, does it still retain orthogonality? Your answer will depend on that. Then question 6. Which of the following is true with respect to Smith method and Clark and Gann's method? Smith method requires more computations. Clark and Gann's method has more computational complexity. Smith method can generate fading waveform for any duration. None of the above. Since it's just a conceptual question, I will give you hints. Smith method uses FFT or IFFT, and in Smith method you can only generate fading waveform for a particular duration, 2 power n times Ts, where n is the size of the FFT used and Ts is sampling period. For question 7, you have to refer to lecture 31. I can give you a hint. C is a true statement, but you also have to check the other statements. Question 8. Consider a base station and a mobile station with 2 antennas. The transmission from base station is picked up by both antennas, which experience different channel conditions and hence different values of instantaneous SNR. The SNR for both antennas is below the threshold at which the signal can properly be detected. Which of the following diversity techniques may lead to proper detection of the signal? Options are selection diversity, optimal diversity, both A and B, and none of the above. Suppose the SNRs are SNR1 and SNR2. We are given that both SNR1 and SNR2 are below the minimum value SNRT, SNR threshold. For selection diversity, the SNR you can get is the maximum of the SNRs of all the antennas. In optimal diversity, you can get the SNR of, which is the sum of the SNRs. Since both SNR values are less than the threshold value, SNR selection diversity will be less than the threshold value. SNR optimal diversity might be greater or might be lower. So, but there is a possibility that it can detect the signal. In the previous question, assume that one antenna experiences SNR above the required threshold while the other does not. Which of the following diversity techniques may lead to proper detection of a signal? Selection diversity, optimal diversity, both or none. So as we saw, selection diversity gives you an SNR which is max of both the SNRs. Since one of the signals has SNR above the threshold, then SNR of selection diversity will also be above the threshold. Since SNR is a positive quantity, the sum of two SNRs is greater than each of the individual SNRs. So the SNR of optimal diversity is greater than SNR threshold, since one of the SNRs was above the threshold value. Question 10. Compute the probability that the output SNR of a selection diversity system is 15 dB lower than the average SNR of each branch and using identical receiver antennas. The probability of outage is P gamma SC is less than gamma threshold is 1 minus e power minus gamma threshold by gamma average power m, where m is the number of receiver antennas. Selection diversity is not helpful in which of the following scenarios? All the antennas are weak in a noise limited system. We saw this is true in question 8. Antennas are correlated, fast fading, and all of the above. If antennas are correlated, then there is a high probability that both antennas both will experience high SNR or low SNR. So there is a chance that both the SNRs are below the threshold. That is, the scenario given in A can occur if both antennas are correlated. And in a fast fading setting, coherence time is very small, so when you do selection diversity, you might not be able to measure, detect, and perform detection within the small coherence time. Consider that BPSK symbols are sent from the transmitter and a 4 antenna receiver is deployed. If only one is used, P is 3.87 into 10 power minus 6 in an AWGN channel. If all 4 are used with selection diversity in a relay fading scenario, what will be outage probability? Given the minimum SNR required for successful reception is 3 dB. P for relay fading for BPSK is Q times square root of 2 times SNR. So the SNR can be found and it turns out to be 10. And in a relay fading scenario, average SNR is expected value of mod z square times SNR of the signal, and we assume generally that expected value of mod z square is 1. That's the usual setup. Again, P outage is probability that gamma SC is less than gamma threshold, which is 1 minus e power minus gamma threshold by capital gamma power m. For question 13, refer to lecture 33. Question 14, consider the case where cophasing is implemented using 4 receiver antennas. Assume that the average SNR of each antenna is the same capital gamma. What is the average SNR of the signal obtained by cophasing? E of gamma cophasing is 1 plus n minus 1 times 5 or 4 times capital gamma, where n is the number of receiver antennas. Question 15, for the different receiver antenna diversity schemes with identical antennas, what is the ordering of gamma MRC, gamma cophasing, and gamma SC? The average HNR capital gamma and M antennas. Gamma SC is gamma times 1 plus 1 over 2 plus etc. 1 over M. Gamma cophasing is gamma times 1 plus M minus 1 times pi over 4. Gamma MRC is M gamma. For question 16 and 17, refer to lectures. That I will end this video. And like I said before, if you have any doubts, you can post questions in the Q&A section of the course. Thank you.